Welcome everybody, how's it going? How are we all doing? Yeah. Ooh, the hero has landed. Okay, so I just realised that I forgot to commit yesterday's or Sunday's work, which is not a big deal, but I need to. It's not a big deal missing one day, but I should really do it every stream. Right. So last stream we got some spheres, ray tracing spheres. Build game. Yes. Oof. So we ray traced some spheres last stream. And then we kind of wanted to see, could we basically get close to free like anti-aliasing of the spheres? And the reason why you want to do it when you render them is because you have all of the context to do it best, right? And you're not doing some system in post where it takes a flat image and then tries to anti-alias that. So we want to try and do it when we render it. Yeah, all these ellipses, yeah. So these are all spheres, I promise. They're just flat shaded. Well, they're not flat shaded, they're... Well, I guess it's flat shading because it's only one object, right? I don't know. They're just, yeah. I'm not sure what the correct terminology is. But, you know, it was quite difficult end of last stream. Because I didn't have the knowledge to sort of tackle the problem best. But I spent some time off stream and basically learnt some maths. So we'll go over how we managed to get this 1 pixel border around the edge. It's kind of 1 pixel. There are places where it's 2 pixels. But it's good enough, I reckon. But yeah, welcome out, Kraz. Welcome, Katim. I can't even see from here with my long sighted glasses on. How's it going? Welcome, Cranston. How you doing? Cranston, I learned some maths. I can now do trigonometry again from GCSE. I haven't done it, but yeah. So I'll go over that at some point. We could, yeah, I think I'll go over it in like half hour or something. Yeah, man, lovely show. This is from, where's it from? From Kenya. Yeah, it's where my yeah, a family member went and brought it back, which is really nice. So basically, I wrote it in a very original sort of. This is the scrub version. This does the if you miss, right? If you miss, this is the sort of scrub version who doesn't really know maths too well, right? And this is the version where if you know trigonometry, you can and it basically is 33% faster doing it this way. So I'm super happy with myself discovering that. Discovering it, doing what people told me to do in the first place, and learning maths. You keep nerd sniping me. I started revamping my ray trace to test out the AA method. Sweet. Yeah, it's cool. Yeah, there's something where I went completely wrong. You know what? I could just start explaining it now. So let's get the drawing going. Then I can delete the old code. Configure that wine. So basically, this guy here is the culprit, right? End of last stream, what were we doing? We were trying to put a pixel, which is like, this is the screen, right? Okay, this is the screen. But what the key takeaway I didn't have is this is the screen in the world, right? It's not the screen in like screen space, right? It's a screen in the world. That's the bit where I was the sort of key thing I was missing. So when I took this pixel and times it by the depth value to sort of imagine what the pixel would look like up here, right, at this depth, right, how big the pixel would be, because, you know, the further it is, the pixel covers more space, right? This pixel here covers more space. in the world, right? So I was timesing 1 by 1,000 because that's where the depth is at 1,000, right? And obviously that is like way too much. But what I failed to recognize is this 1 pixel isn't a length of, it's not a unit length of 1. What it is actually, so this here is the distance from the camera to the near clip plane, right? And it is also, there's the near clip plane. It is also the height. That was a terrible one. It is also the height as well. That distance there is also the height. It's obviously not to scale, but there's the near clip plane. It's also the height as well. So when you know that, you can basically translate here. So near clip plane height, right? So in our case, it's 1 divided by the height of the output dimensions. That's the side of a pixel in clip space, right? And then we can times that by the depth to know about how big a pixel is in the world. And that is basically the bit where we were missing. So this will be like 0.001 or something. Then you times that by 1,000 and then it gets you to 1, right? Well, it's kind of, and that's the reason why, like, basically comparing it against 1 was working last stream. Yeah. So this is why when we did distance from edge, when we said, hey, if distance from edge is less than or equal to 1, it was mostly working. It's because of that reason. It was already sort of, like the sphere was at 1,000 distance. So, yeah. So, basically this version here, it sounds like the pixel size in world space could be dependent on which projection you're using. Yes, it is dependent. But that's why we've used this function, right? We're doing it, the near clip plane I've tested out already. So we change the field of view, right? We change that to, let's make it really wide. If we zoom in, it's still a pixel. Well, about a pixel, could be 2 pixel, because we've coded it for that. Yep. So that's good. I spent ages testing that just to make sure it was right. Right, what else is the thing? Yeah, so the way this method works here, this was the, like, I don't know maths version. Yeah, this is like all I know is vector maths version. So what we were doing here is, so we've got the ray origin, which is here. Oh, that's where my face is. So let me move it. All right, it's here. Right. Right. So this is where the ray origin is, right here. Okay. Ray origin to sphere. We get a vector going from there to there. Boom. So to the sphere's center. Yeah. Then we got the closest point on the ray by doing some, by doing the dot product, right? And what the dot product gets, it gets you the distance projected across the ray direction. So the ray direction is this white line here, which I'm going to paint over. Yeah. This is the ray direction, and we're reprojecting it across there. So that gives you a right angle triangle, right? I'm basically spelling out all of the problems with this solution. And then we got this closest point here, which is this purple guy, right? And then what we did is we basically then, this, as you can tell, it's super overkill. Then we had this point and we had this point. We could take the two away, get that vector, and then we could sort of like normalize it, get this normalized, and then sort of work out this point because it's basically the length of the other one, take away the radius or something like that. I don't know. But anyway, we get that point, and then we can do basically the length between these two, and then we could get the, as you can tell, really overkill. then we can tell if this is wider than a pixel on the screen. Wait a minute. Yeah, if this is less than a pixel on the screen, then we can mark it as blue, and then we can do the special anti-aliasing, right? So as you can tell, that was a lot of steps, and it's quite overkill, a lot of length operations, and, well, only one length operation, because it was kind of optimized. But, so the real solution is dead easy, right? Just involves some simple trigonometry. The problem with trigonometry is that you've got a bunch of different ways, depending on which parameters you've got different ways to do it based on what parameters you have. And the hardest thing is like figuring out what parameters you have. And obviously there's a thing to remember to do it, but yeah, also you can Google for it. So what we have again is that ray origin to sphere vector, right? And this is the hypotenuse, I think. Hypotenuse, right? So it's the one opposite the right angle. And you know it's the right angle when we did the dot product. We make it the right angle, right? So we did the dot product with this vector that was just drawn with this ray, the normalized ray direction, right? And that has already given us, right, the length of this side, right? By literally just having this vector and a normalized vector of the other one, right? We haven't recomputed anything with this ray direction. It was computed once at the start of the compute shader, and by literally just doing the dot product, you already have the length of this vector, this edge of the triangle, right? So we have this length, but we don't have this length here yet. It's just in vector form. So we take the length, get the hypotenuse length. Hey there, Exist, welcome. Yeah, day's going good, thank you. Well, yeah, mostly good. Super busy day at work, but yeah, other than that, pretty good, thank you. How you doing? So, but we didn't really have the length here, so we did the length operation, but we didn't want to do a square root. So I did the length squared, so I left it in squared space, right? The reason is because this is where trigonometry comes in. Now, obviously, I didn't do it this way at first. I optimized it later, but, you know. So now all we need is the size of this. Well, not all we need. The next thing we need is the size of this edge, right? And this is, remember, it's got to be a right angle triangle trigonometry. So because we have the hypotenuse length and we have the adjacent edge length now, right? Basically the formula is hypotenuse length squared and adjacent length squared. Obviously you take away that one from the hypotenuse one. That is the length of this guy, right? That's it in squared space, right? So you have to square root it, but we want to avoid the square root. So we leave that one here, and this is the closest point on the ray to the sphere distance squared. So it's literally this length here, right? So now we just have to compare it against the size of a pixel plus the size of a pixel at this depth, like how big is a pixel at this depth, plus the radius squared. So we basically square the, where is it? So we add the radius here to the size of the pixel, and then we square it, and then we do the comparison, and then that involves involves no square roots. It's just subtractions, multipliers, and adds. So that's pretty decent, and we're able to get it down to about, from this to 0.239 ms to 0.179 ms, and this will get us our outline around this. This basically says, hey, our ray casted, our ray missed by less than or equal to 1 pixel. So I could just do this. So yeah, that's basically the story behind the solution, and I'm glad I figured that one out eventually. So we should be able to get basically close to free anti-aliasing when we, well, actually no, we should test this out. How quick actually is this? If we, what is the actual cost of this? And but again, the reason why we want to do the anti-aliasing here is because rather than doing it over the whole screen on a flat image where we don't really have much context, obviously you can get like depth like a depth buffer and stuff like this, but instead you're doing it when you actually draw the sphere, you have the most context then. So it should hopefully be better, but we'll see. So let's run this, right? We're about 0.177 ms to do this ray tracing sphere. Let me just actually change the field of view back. Oh, that was back. I didn't compile it. Right, 1779. Yeah, 179, 0.179 ms. Yeah, on Discord you wrote that you tried to do 9 spheres per pixel and it took 0.1. But how 8 spheres on the whole screen? Is there only 8? Did I miscount? No. Maths is not my strong suit, clearly. 3, 4, 5, 6, 7, 8, 9. No, there's 9. 3, 6, 9, right? Oh, right, okay. Yeah, there's 9 per pixel. So what we're doing is seeing this compute shader, we have this array of spheres, right? This is ran per pixel. So per pixel, we go over every single sphere right now. And we need to obviously optimize this. But yeah, that's basically it. Yeah, so maybe we could whack in a quick tiling. I have put in the stream that I want to do some models, but then again, I just thought it might run it really long. We might do a very low resolution model, and then we'll make it out of a sign distance field or something. That'd be good. Okay, so should we finish off the anti-aliasing then? So how are we going to do the anti-aliasing? This is where the fun begins. So because now we can detect where we have missed, because now we can detect if we miss by a pixel, right? We can now mark this guy as the one which is closest, but we've just missed, right? And then if it hits something behind, we're going to blend this guy's color in with this guy's color using some front to back blending, which we've already got from the UI code, right? But then you might ask, what happens if we just miss 2 of them? Well, the way we're going to do that, so the way we check these spheres are out of order. So we'll just grab the closest one, right? Say we just missed this one, and then say if we just missed this one and we hit this one. The way the logic is going to work is we're literally just going to make this one the near miss sphere and this one the hit sphere, maybe. Should we? No. I don't know actually. Should this one be the near miss sphere and that one the hit sphere? Yeah, this one should be the near miss sphere, and that one be the hit sphere, I think. Yeah, I think we'll do something like that, and then we'll just basically blend it later. So it's quite simple actually. So shall we bring back some colors, and shall we do a very simple sort of lighting thing? So So let's just do that very basic lighting thing, right? You know, the n.l thing, right? Normal dot with a light. So we'll have some sort of like light direction. My thought is that the hit is to hit the near miss and then recursively recast from that. Yeah, so the problem if you did it that way, you have to be in order. You have to have it sorted in order, right? And I don't want to do like I think it would just be cheaper if you didn't sort, right? And I don't think the effect would be like definitely that would be more correct, but I think the sorting would also just take more time, especially when you want to try and aim for a very high high number of spheres, right? Now by hitting process, only traced. My thought is the hit. You hit the near miss. No, by hitting process only traces to the nearest. Every sphere, each recast. I'm not sure if I understand because you have to trace every. You have to trace. You know, you're already tracing in a line, right? You're just basically doing a test against every sphere if the ray hits the sphere. So you have to go over every sphere at least once, and we're gonna make this less by binning them into screen tiles later. You just do a full ray trace each time. Right, so you're saying go over all of them again. I'm not sure if that makes sense. You have to go over it in order if you want the blend to be correct. I think we can get away with it being slightly incorrect. Because the chances that you'll have two near misses is not very big. But I think someone can find it. Though if they really tried. It could definitely be a really weird glitch if people line it up right. But the idea is they'll be so small that it hopefully shouldn't matter. So here's our fixed light, right, just down direction. Maybe we'll do, I don't know. So you do the dot product of the hit normal. So we haven't used the hit normal, so it actually could slow down the perf results we've got. So you dot those two guys. Now this would be -1 to 1, and basically 0. You want to clamp it to 0 to 1, like a full-on clamp. And then basically just multiply that with the color. So you go something like mul-s. Yeah, Kranz, I'm not really sure if I'm understanding exactly what you mean. It's yeah, I'm not sure. Like, are you saying go over all the spheres again? If you... Yeah, I can imagine. Yeah, that's fine. Or if you have an elegant way of describing it, feel free. Yeah, I think the way I've got it like mapped out in my head is it should be good enough, but we'll see. Maybe you can help me improve it. Float does not implicitly cast to... Oh, okay. Because someone made it float 3. Oh. Right. Okay, so that will get us a nice bit of lighting that's upside down. Because somebody didn't do the maxing. Max F32 times 2, 0 Ta-da. And I think it's upside down, right? As we saw. Right, so now they're not just circles, people. This is part of the reason I want to do this, because it's very easy just to be like, this guy's doing circles which look funny. Why is it upside down? Is my space wrong? What? Why is... the way the normal is made is wrong, right? No? I am confused. No, it's just a direction. No, it's just a direction. Like, you're just saying, like, I've got... Probably, I should have really probably drawn this. So you got your sphere, and it has a surface normal of going that way, right? Maybe it's not a good one to draw. Maybe it's going that way. There we go. So you got a light direction coming down. Oh, I didn't... Okay, I should have drawn it out, then I would have done it right. So basically you're saying... Yeah, I've got to negate the thing. So if I say the dot product of this vector and this vector, they're both normalized, by the way. This will give us negative something, right? Wouldn't it? So obviously if it's going this way, it'll be 0, dotted with a light. Then if it goes upside down, it'll be positive, right? So it's just very basic stuff. So if I literally just do the negate there, that ought to be good enough. Wait, I flipped the light. There we go. Sweet. So now we've got our lighting. You know, it's, as you can tell, it's the finest lighting you've ever seen in history. But maybe we should bring the light a little bit closer so we can see the anti-aliasing take more of an effect, right? So what we're going to do is we're just going to normalize this so I can be a little bit lazy on how I assemble these numbers. And we're going to say, hey, you go positive along the x, and you'll go like probably twice as much down. And then that'll bring it, the light, a little bit, like it's pointing towards the scene. Well, okay, guess the way you guys are looking, it's pointing like that way, right? It's kind of brought and it kind of feels like it's brought closer to the camera and pointing down and into the scene. Hey there, Not So Red, how's it going? Doing good, man, doing good. Yeah, just gonna finish up this anti-aliasing stuff, but yeah, just been, you know, I did learn some trigonometry again, Not So Red. You should be proud of me. I did GCSE level maths. And it went good. The code is simplified. Yeah, we learned. Learned. Yes, we learned it. Damn it, Americans. You know, here's the thing. Not sorry, you're not even American. You need to learn true English. You need to learn. But yeah, things are going good. How's things with you? So yeah, we're just gonna now talk about how we're gonna do the anti-aliasing. Actually, no, we already kind of spoke about it, right? We've got the nearest. We need to keep track of the nearest near miss, and right. So we'll say like. So do we just need a color? Is that right? So you start off as fully opaque. Near miss color. So we'll say fully opaque, something like that. And we'll just check the alpha if we've got an actual hit. So this one's like, oh, I found a hit. My near miss color is this guy here. Right, so this kind of like, we got to make this into a function. But for now, actually no, we'll make it as a function. So we'll say like f4 sphere color count sphere color. We need the hit normal. We need the packed color, and voila. By the way, what GPU do I use? English is not my first language, so yeah, I can't argue with that one. That's pretty cool. You can actually know 2 languages. And you can actually understand me speaking English. Like, the fact you can understand an English person speaking is pretty good. Because we speak, can speak quite fast and have all this slang, lingo, which is not correct English. Must be a lot of work. And also the language doesn't make any sense. Have you seen it? Like, you can literally hear someone say a word, and without any context, you'd be like, is it this word, or that word, or that word? And there's like 3 or 4 different words with the same way to say it. You're like, great. What GPU do I use? No, this is all AMD RX 6600. Let's just spell it out. So we're not using ray tracing, but we're ray tracing. I like to say things funny, but yeah, we're just using compute, and we're just casting the rays manually. So we're not using the very overcomplicated API which they want you to use. We're just doing it using compute shaders, which is basically getting access to all the multi-threaded stuff and just doing it manually, because it's kind of, we're seeing if it's good enough, and that's something we didn't test. We didn't actually test. Right, can I just compile this? We didn't test what happens if we remove the anti-aliasing code, right? And what sort of performance we get. What the hell is this? Oh, I need an S. Oh, right. So the thing is like, what happens if we compile this out? Maybe it's already compiled out now, because we don't actually use the information, but let's... Right. So when I said free, it does take up... So this is 0.129. Now I put it back. How is that even faster? But the red outline around it is faster, is it? GPUs. You are confusing my brain. Ended up faster doing it. Okay, don't ask me why, but apparently... What am I setting? Wait, let me take... Let's set the color as well. 2 seconds. Right, okay. It was doing some optimization where the color wasn't set. So yeah, the color wasn't set, so it would set the something to do with the texture was not happening. Yeah, I can't fully explain it, but okay. So it does add, so we're going towards that 0.196 from 0.129. Right, so it is about 50% slower doing this. Maybe we can make that better. But yeah, that is fine. Why is that right? Why did it say 51%? It should have been like 49 if anything. What did I punch in wrong? Oh no, no, that's right, that's right. Sorry, I was just getting my ratios wrong. Yeah. Right. Well, Unreal Engine 5 Lumen also do without ray tracing hardware and add bridge the later versions. So basically, default approach to modern engine. Maybe. I don't know. Ray tracing is becoming quite more widely spread. Yeah. And Lumen's doing ray tracing for lighting. This is ray tracing for rendering. So it might be slightly different. Hey there, Nico. How's it going? Like, well, actually, no. Maybe it's the same thing. They're ray tracing their scene and probably producing. I'm not sure the way the implementation works. Okay, so now we've got a near miss color. We can say if there's a near miss, do a blend. So where's the blending? Wait, we should have a closest near miss, isn't it? Closest near miss depth equals infinity f32, right? So we just want to we say if this is less than, wait a minute, if our depth is less than this, we say our equals depth, and then we do that, and then we say we need to say there's a hit once, but let's do it there as well. Okay. Do. So the other thing we're looking for as well is we actually need to find the closest hit color, because they could be behind. Yeah, we're just overwriting it, which is not good, right? Because if you run it, you'll see that these guys just overlap each other. Like you've got two flat drawings. When when really this should go a lot closer here, right? And we're hopefully gonna get rid of these horrible edges here, right? So let's see what happens. Right. So now we need our closest hit depth, and it's the same thing. Closest hit depth and that goes on to color instead. Very, very nice. Now at the end, so if we run this now, we should be seeing an improvement at least. Been debugging some stuff lately with Beehive VM hypervisor. Yeah, I remember hearing about that. And hitting the same bug that I fixed a few days ago again. So annoying. Oh, yeah, it does sound annoying. Yeah, I've heard some good things about the FreeBSD systems. You got like Beehive, the VM hypervisor, and you got Jails. And I've heard it's like really good technology, but I've not used it. Um, it was pretty cool stuff. Yeah. Hmm. So you use jails for basically running instances of old FreeBSD versions, right, in containers, and then you use Beehive for other operating systems, right? Is that correct? Um, or can jails do more than that? So you've got the hit, right? So now it should run, should TM. All my days. Did I? Yeah, maybe I didn't get that component before. Right, hit dot t. T is a bit of a T is the depth, but anyway. Right. Okay. Here we go. So now we should see these better, as you can tell. Remember that? They were overlaying like they were just circles overlapping each other, right? But now they sort of merge together, right? Proper cool. We're not seeing any sort of jagged lines. I was hoping to see some jagged lines, but we're not. So now we've got to fix all these jagged lines and finish our anti-aliasing algorithm. So here we go. Wait, that's made it quicker. That's literally made it quicker because we're doing it less times. We're doing less of these. Calculate sphere colors. Pretty good. Optimization. Without even trying. Doing less of these boys. So, right. So the next thing we need to do is get the blending code from the UI stuff, right? Here's one I made earlier. Front to back alpha blending. So we got a hit, right? Bearing in mind, if we got a near miss, that's kind of a hit, isn't it? Yes. So the hit color should default to black. Awesome. Now the next thing to do is front to back alpha blending. So destination color. So we're blending the one at the front, which is the near miss color. So only if there's a near miss, you do the front to back alpha blending. So if near miss color, bear in mind we might do some blending also. I should make this into a function, right? You know what I mean? Know what I mean? Yes, jails are glorified cheroot plus networking control knobs, resource map control, whereas Beehive is its VM hypervisor, server is running it. Sweet. Manjaro. Oh yeah. I support 4090 because of Raytracing performance and tensor teraflops instead of 4090, and now suffer from horrible bugs in Xorg and not even Wayland, which isn't functional at all. Sadage. Oh, that sucks, man. Yeah. In Xorg, not even Wayland. Crap, have you tried Wayland out? That's really bad. Yeah, AMD's better with the Linuxes, basically. You know, people like to hype up NVIDIA as being awesome, but I have a bit of a different opinion about that. you know, AMD are doing the best at the moment in terms of like, you know, being more open for developers, and you know they give their instructions to architecture. They give basically implementations of some upscaling technology, denoising, and loads of other stuff that people basically implement, like sorting algorithms and that on GPU. They're already hand optimized and stuff like this. Whereas you see less of that from NVIDIA, and NVIDIA make more and more specialized hardware on their GPUs, trying to sell people on it. Whereas AMD kind of take the approach, from what I understand at least, more of a generalized hardware. So they don't really specialize for like uniform buffers or specialize for Texel buffers, or it's just basically a code that, like assembly code that just runs on a compute unit, aka a compute shader, right? They don't they obviously have specialized hardware for like rasterizers and stuff like this, but it's mostly just compute. So that, yeah, I kind of like AMD's approach more. But I know a lot of developers basically default to NVIDIA and that sort of stuff. Probably just because they're the most powerful. Um, but yeah, AMD's not that bad in terms of performance. They're just not the best. You know, it's basically it. No video, yeah. Yeah. They promised Wayland in 545 plus drivers, but they're missing synchronization primitives. Right. Oh, that's horrendous. Yeah, I don't know why. They also came out saying they're making like record profits or something like this, and they're, you know, or I forgot what it was now. There's recent news about Nvidia or something just doing really well, and I can't really say exactly. Once you've sorted the ray tracing, what's going to be the next implementation? So once we've tested out ray tracing, the next one is going to be trying to see if we can write a little sphere rasterizer in compute, not using ray tracing. I've seen some implementations online. I want to see how fast that is, and we're going to be using atomic min to basically deal with the overlap of two compute shaders writing to the same part of the texture. Just use atomic min, which seems pretty quick. But you want to try and avoid the amount of overlap you have between two shaders trying to write, so the atomic mins don't, because otherwise it forces synchronization between the threads or whatever. So you want to be careful about that. But yeah, that's what we'll be doing next. Right, so this is right front to back blend. Static, float 4. So doing a blend front to back. Front front pixel, back pixel. Oh yeah. Blend pixels. Where are you from? Earth. No, I'm from Kent, UK. Right, so destination was gonna be the back. No, it's the front. What is it? You're doing front to back. So the one. Yeah, you get the front back. Where it returns. Yeah, it's not really new front. But yeah, so this would be front. Then, oh my god, I'm from Mars. Whoa, we're like neighbors, man. Alright, that ought to be good enough. We should really enable the UI again just to make sure we haven't messed it up, you know? When I researched on GPUs, I found that 7900 XTX is basically a matrix, has matrix instructions and ray tracing acceleration instructions too. It's not that different from 4090 really. Yeah. Yeah. I wonder how much of those you can use in compute. Definitely the matrix, but I mean the ray tracing. Right. So the front pixel is that one. And your back pixel, that's it, right? Okay. Let's go full ham. So your front pixel, so you're gonna say color equals blend front to back. Color, the near miss is at the front, and the color is there. See, code reuse just creates all this extra stuff, you know. So front to back alpha blend, boom. Bob's your uncle. So we'll run this and then we'll quickly check to make sure. Oh boy. Why is it jittery? So I quickly just want to disable this and make sure that we've got, it's blending a lot. I thought we said it. Let's re-enable the UI code because I want to make sure that we've done the front to back blending right. Like we've changed the code right. I just want to quickly double check that. That looks wrong. That looks more orangey. Whoopsie. Oh. Urgh. What have I done? Right, so we're going to undo what we've just done inside here and then bring it. Oh. Haven't I got any music going today? Where is the music man? Where's the Stone Rebel at? On video side, you can't use Raytracing instructions as intrinsics directly, although through optics or Vulkan provided API. Oh, yeah, right. That makes sense. Yeah, I guess. There's also another way to requiring mesh shaders. What do you think they're using them for? They're using them for probably the LOD stuff. Like, what was it for? So mesh shaders. Yeah, I forget exactly. I can't really describe it exactly. I have to double check it. But yeah, mesh shaders are like a bit of a weird one. Like, you can probably get away with just doing the mesh shader itself in compute. Like, people have done that before the mesh shaders came around. And mesh shaders haven't really got that good hardware support yet. They obviously work on the latest and greatest in NVIDIA and AMD, but they're not really widespread other than that. But yeah, people were already doing what compute shaders were doing before. Right. What is different from this? What did we say again? Destination color was front. Is it back then? Did I do my front back the wrong way around? I don't even know, man. Right, let's do another version. Front. They look the same. What's going on? Should we get this code and take it back? Just throw it into the UI one. GFX shaders. Oh. So it's not the front to back rendering that's the problem. It's the new... Right, we're placing pixels down with the sphere ray tracer. Right, that's the problem. No? Oh no, we did the we fixed up the RGB colors, isn't it? The sRGB stuff. That's why. Okay. We fixed up the sRGB. We didn't test that again. That makes sense. Okay. That's fine. Right. That's fine. Okay, so we're doing that front to back blend. Why is it jittering all over the place? So we should be seeing some alpha, like... So that should be see-through. Right, we need to start off as a my sphere color is red. My sphere color is red. So we don't select it. If we don't have that, it looks fine. But as soon as we have that, it kind of looks a bit weird. These sort of go a bit transparent. Oh, the normal. The normal is not set. Right. So we've got to compute the normal. That is not set. That's the reason why. So how do we compute the normal? It's hit position, sphere radius. This boy. So we recompute the normal. What the hell's going on with syntax highline? Damn you, Neovim. Normal. I don't know anymore. Hit position. What's our hit position going to be? Where's the... We could do the depth, isn't it? Ray direction, mole depth. Wait, that's a sub. Yeah, we need that. Divided by that. Right, it's not going to be normalized though. Ray direction. Mol S, F3 times 2. With the depth. Now it's not going to be normalized, so we need to normalize it. So that's going to be good enough. Right, so we used normal. Oh yeah. So run that. Boom. So we're not seeing the jitter anymore. So now we just got to see if the blending's right. It's not right, is it? Now we need... Right. So we're getting the right color, sort of. No, you know, the color's not right. Color's a little bit off, not gonna lie. But yeah, now we just have to make sure we get the right blending. Seriously, what is going on with Neovim? Let's close the buffer and open it again. Now we just have to make sure that we actually have an alpha transparent C applied to the near miss color, which we'll sort out. All right, we're back. Kata MOI, that's how you say it, Kata MOI. In OpenGL, when you draw from two different PNGs, you're essentially drawing textures from multiple times. Recommended max cap is 500 in OpenGL before you run into issues, right? What if the two PNGs... Well, it's 500 textures. That I don't know where that number comes from, not gonna lie. There's no difference between the aperture and these, right, except the size. Add this is up to 5 times. I don't really know what the idea is with that. Yeah. I would say try to stick with atlases where possible, have the least textures as possible. Um, but thank you for drawing me, by the way. But right, active atlases. Yeah, don't worry about these. Like, I think you can have up to about like 10 and it's probably fine. Don't worry about having multiple textures in a shader is fine. You can have tons in Vulkan and tons in OpenGL nowadays. Um, but yeah, somewhere in the ballpark of 10 active textures at a time per shader is fine. When you start to go over that, it's probably a little bit weird, but it's probably manageable. But yeah, the amount of textures in GPU memory, just have as many as you need. Try and bunch them into a single atlas where possible. But if it's too much of a pain, don't bother doing it, right? Yeah. Um, yeah, I would say just don't worry about it yet. When you start bumping into issues, think about it, I think. I'm using tree sitter. Yeah, I think I'm using the tree sitter for syntax highlighting, yes. I went all in on the Gen Z options since I was sitting there in the millennial options and I was like, you know what, Gen Z it up. But yeah, since I am borderline Gen Z millennial, you know, decided to take a dive. So this is not really ray direction times depth. The color is a little bit off. And I can't, like, that's fine. It's when you start getting here. Ray, you got the right angle triangle. Ray direction at that depth. Right angle triangle. Oh, you didn't normalize it. Right, it's the way it's doing the division. Right, it's too far away. So we divide it by the new size. This one is squared distance though. Problem is it's squared distance. You might have to square the vector. Do a square function. I have a square function, okay. That's not correct. Wait, square gets rid of the sign, doesn't it? Of course it does. So if I square root that, it'll be correct. Wait, square root f32. Get rid of the norm. You're doing a square root anyway. So no, we're still sort of getting the discrepancy here. And why is that one drawn over it, you know? It's a bit weird. Ooh, we only want to draw it if the... Oh, that's where the discrepancy is coming from. Right. So this is probably better because normalize is more expensive. This is probably quicker if we just square root this anyway. So we'll keep this. We shouldn't be doing the blending. We shouldn't be doing the blending if and near miss, closest hit, is less than closest hit, near miss depth is less than. Yes, we only want to do it if the near miss is closer to the screen. That's where the discrepancy was coming from. Okay, so we've got a better color. It's a little bit off still, I think, or maybe that's just because I'm noticing. I don't think it's actually off by much. Yeah, it's not off by much, tiny bit off, but I think it's doesn't matter because it will go transparent anyway. We should check for half pixel size, not 1. Also, maybe weight by the nearest miss color by 1. Ooh. Yeah, I haven't quite got to that bit yet, but I'm just about to go and do that now. The near miss thing, near miss weight. Should we check for half pixel size, not 1? I was. You have a sphere, and your ray misses by. No, it's if you miss by less than a pixel, and then you weight it by 1 take dist. Yeah. We should do. Yeah. So we've got to put in a color now. So you say your color is pixel size plus radius square root. So what we're trying to figure out then, the weight, isn't it? Like how much we missed by. So this gives us how much we missed by. We just have to rethink the problem. So you want to say missed, but it's not in pixel. Missed by a distance. But you're working in squared space. Right. So we'll just do it in here. It's fine. So we should really I'm gonna have to recalculate how much we missed by. We could do. So you got to do a divide by depth to bring it back into. Divide by depth and times it by. Yeah, there's right pixel depth. We'll get this back in. Plus radius. Oh, so we need to calculate. So missed distance is the square root of that. So that's the distance from the ray. Let's get the image up. That's the distance from here to the ray. So so square root that, so it's that distance. Minus the radius. And now that's how much you've missed by. Right. That's how much you've missed. Yeah, that's this green thing here. As a distance. So we've missed by that much. So we need to bring that back into into pixel, into screen space. So you will do, so this is in world space. So to bring it to screen space, it is this divided by depth, and that will get you into near clip space. Right, that's clip space. So that's the near clipping space. Then we need to multiply it by output dims. Wait, is that right? What is this? Pixel size and near clip plane. So you probably need to multiply it by... divide by that, isn't it? Because that's how big a pixel is at near clip space. So we divide by that, it will, and it's the same number, it will give us 1. Right? Yeah, that makes sense. A lot of divisions, but should be fine. TM. So there's your depth. So that should be near-miss, right? And then, so obviously if you miss by a whole pixel, you want it to be basically opaque. Sorry, fully transparent. So it's one take, and there's 0, you want it to be transparent. So it's one take that, and then you want to make sure you max it with 0, because technically the code is a little bit wrong. Because the way we sort of do the test, we do the test in world space, and the pixel in world space isn't really like a pixel. Like the size, like we just say, hey, how big is this pixel size in world space? But it's not really square anymore because of the screen's aspect ratio in the world, so it's a little bit off, and sometimes we get 2 pixels, so we have to max it with 0 to make sure it doesn't go underneath or negative, right? Yeah, so that should be it. Let's see what happens. Right, doesn't look right. We can debug. So we can just do GPU print hprintf, and we'll just debug print this out. Alt B good enough. Right, so these are the values we're getting. Probably instead of projection, the size out to the world. Projection both points down to the near plane makes it easier to get accurate pixel distances. Yes, and since we know how to do that now, it's probably not that bad, but the problem is, wait, probably instead of projection the size out into the world. Yes, that is true, but projecting it out into the world is probably cheaper to do as a per pixel operation, and you'll be off by 1 pixel sometimes, so you'll get an extra pixel that will come in here. So this here then doesn't use any of the information that you use to calculate that. It just brings back the proper information that you would have used anyway back into screen space. So it should be, wait a minute. Wait a minute. So what I was saying was wrong. It never goes over 1 anyway, or below 1, below 0. Well, it'll never go below 0 anyway. Yeah, I think that's good actually. Yeah. So so we don't need this check. So why is there an issue then with the code? Should we not do... Something's up. something's clearly wrong. No, actually no. We would need the max because it could technically be wrong still. Yeah, because it'll come into here. And this could be off by a little bit. And the rabbit hole gets deeper. Oh no, Nico. What points to limits and so a buffer overrun here. Right past end of buffer. There we go. Those are... Yes. Yeah, those guys will typically, like, mess you up in it. Stomp on your memory, and your memory would just be, like, garbage. Oh, these are someone else's bugs. Right. And you got to deal with those first. Oh, C, the real language. Yes, to see whether I'm doing dumb stuff, I want to use address sanitizer. Exactly. Yeah. Oh my days. So is it something I'm not doing with... If it's greater than or equal to 0, it's fine. Near miss depth is less than the hit depth. What's going on? Could it be something to do with that? Right, should we change the color? Because I'm a bit... Like, should we make it obviously wrong? Because I am a bit confused. Let's just make it white, right? Blinding white lights of edge. Right, so as you can tell, it's there, but it's not becoming transparent. I think the ray to sphere trace should be able to cheaply get you both closest points on the ray and the sphere, projecting them to NCD and normalized device coordinates on the ray. Sorry, projecting to normalized device coordinates should be a single matrix effect multiplied per point. From there, a single distance may be still more expensive than what you're doing anyway. I'm going to try it. Just want to see if you can spot any obvious flaw with it before I sit down to do it. Okay. That's cool that you're going to do it. So the rate sphere could do a cheap... Yeah, because you calculate the midpoint, isn't it? Whatever it... Was it you who gave me the code? I think you gave me the code, wasn't it? Or was it someone else? I forget. There's many people I speak to, and it's hard. It's a bit blurry sometimes. But yeah, we calculate like the midpoint here anyway, isn't it? Yeah, so the compiler is probably reusing this because it all gets inlined. I've already thought about this. This probably gets inlined. But yes, it's probably better to sort of make it become part of all of this anyway. Um, yeah, closest point on. Yeah. Yeah, it was you. You gave me the quick one, and I was like, whoa, that's way better. Then projecting it onto normalized device coordinates. Yeah, maybe. You could also project it to screen space and you get the pixel. It'll be a pixel. That's fine. But yeah, that is this for people who don't know, this cross here. Well, it's the length from here to here, right, as a scalar, along the Ravec. But yeah. Yeah, go to screen space and do the check there. But yeah, I think it's probably fine. I think, yeah, so in terms of like the optimizer is going to do this, like reuse that and this here, which is the thing, this is the midpoint, right, that we saw earlier. The optimizer is going to definitely reuse that because of SSA, right? Single static assignment, it will work that out. This is inlined, right? It's shader code, it's inlined. So the question is really is like, is this maths quicker than the one you're saying, basically? So you have to go the other way. So if you can have an inverse matrix that makes it just multiplies and adds, then yeah, that could possibly be quicker. Hey, Glorious, how's it going? Well, no, it'll be about the same, maybe quicker, with and more precise. Right, we have to have the matrix. Oh, it's just scalar maths, right? Yeah, I'm doing it in World. But on C++ templates, the performance is going to be shit away. Okay. Ah, templates. There's too much PP in it, you know? How's it going? It's going good, Gloria. So we're just literally putting the finishing touches on this anti-aliasing thing. But yeah, things are going super good. I did maths. You should be proud of me. Trigonometry. So yeah, we're just trying to blend this, make this more transparent, but we kind of what's so wrong? Front to back. Right, so if we hard code this to like 0.5, if that don't work, then there's a problem. So if front to back, should we switch the front to back around the other way? See if that's the problem. Right, I'm starting to see something. Yeah, I'm seeing some blend. Well, I can't even tell because it's so blurry because they use linear sampling on the zoom tool. These people. But yeah, we put the color back. Oh, can you see the anti-aliasing? That looks good. So something's up with my blend function. We did it, guys. Anti-aliasing for basically free. Well, it basically is free because we put if statements around more code because we did the anti-aliasing. It made it even faster because we did less computation. But yeah, technically if we remove it, it'll be even faster. We should do some tests. Let's get Creator open and zoom in on this guy. I'm so proud that you spent about 4 hours understanding it since I'm a dumbass. I don't know, man. Like, yeah, I spent about 3 hours, well, 2 hours on stream being a dumbass. And then after stream, I was like, right, I need to learn GCSE maths again. And then we did it. So there we go. So this is what we were working hard for the past 2 hours on this stream and 2 hours on the last stream. is this lovely, lovely, lovely anti-aliased edges that we couldn't probably, I don't know, yeah, I'm not sure how good we could get it if we did it as some post thing, but you know, we're trying to do it when we, just look at that, man. Oh, so let's keep going with the sphere. Many sometimes blows up, gives up. Damn it. Yeah, man. Think about last stream how this all looked pretty bad. Loads of flat. But now we've got a little bit of test lighting. AA. Oh yeah. So there's still one thing on a test. My front to back thing, I put it the other way around. So what have we done? Is the question. What have we done? Did I get the front to back the wrong way around? Can I go back to my UI a sec? So we're in front to back. Yeah, I think I did the front to back the wrong way around. Do you have a front? Yeah. Right, let's redo this the other way around. Front. Is that right? Because final color. What was final color? Final color was the original front pixel. I don't see. Maybe my UI was wrong. Like, and I changed it and didn't test it again or something. I really don't know. So we got to quickly just test my UI because. Right, can we do that? Let's enable some UI. Let's set something to be transparent. Can we set the text to be half transparent? FG. Shoot is going on. I didn't see it now. Right, swap this back the other way around. Then it works. But it's... Let's take it down to quite low, 16. That works fine. What is going on? What is going on? When you colored edges, that should be anti-alias white. The sphere intersections didn't show up. Do you know why? When you colored edges, anti-alias white, sections didn't show up. What do you mean the sphere intersections didn't show up? What do you mean by intersections? Do you mean the... Yeah, obviously we're not getting anti-aliased here because we're done against the image. No, we need to make sure that we take the color of the UI. Well, okay, technically it's the other way around, right? This should be rendered underneath the UI, but... where the big sphere overlap intersect. Right, this thing here. There should be right, I see what you're saying. when you colored edges, that should be anti-alias white. Okay, I got you now. Yeah, that makes sense. I should have picked that up. Didn't not show up. Do you know? Yeah, they do show up. There's a crease. Yeah, there is a crease, but I guess they're anti-aliased. Hmm. Yeah, but it's not a miss. It's not a miss. This is not a miss. Oh yeah. Because they're not misses. Should I color it white again? We can see it. Yeah, because these are not misses, right? They're overlaps. So the miss actually would go inside here, right? That's correct. Yeah, that's why. So it would hit this one. So it will miss this one and count it as a miss, but this one will hit and it will be like, I am closer. Yeah. Yeah, exactly. Yeah, I've got an if statement here. If the closest, only do the blending of the closest near miss is less than or equal to the closest hit. Yep. So the question is, why is my front to back right and wrong? I have no idea. So you pass this in as the back color and it works fine? Wait. Oh, sorry, I can't tell my UI in the way. Can I get my UI out of the way? Yes, this doesn't work. Because the alpha doesn't get counted. Where is it? Is that right? Your front alpha. Wait. I'm in the front. My front alpha onto the back. RGB. What? And then my new alpha. Right, because back RGB. Re-multiply the alpha onto the back. One take this. The one in front. Because the front one's already been rendered. That's the problem. So we need to have pre-multi... Wait a minute. The alpha needs to actually go on the back one. Okay. Yes, this is correct. But technically the alpha needs to go on the back one. Based on the miss. So what so the other thing as well is like, this is probably expensive recalculating it all the time. Every time we've got a new closest. So we could probably optimize it. And only do it once, and then also set this in the right place at the end. So which one? So array direction, that's the fine. Depth, that would be the closest depth, so that's fine. Sphere center position. You don't know the sphere, you'd need to keep that. You need to keep this as well. Wait, would you? Yeah. So you do that just to calculate the normal. So you could just keep the normal and save on calling this function multiple times. You could save out the color as well. Yeah, I think it's a bit of an optimization we can do later when we get multiple spheres going. But for now, we're just going to store the alpha. So you'll just store alpha. And if this is true, then color.alpha equal alpha. And that's correct. Wait, is it? No. Jump the gun. Near miss is in front. What? What did I do wrong? Alright, this should be if this is less than that. It could just be done in one check. Why aren't we getting any more? What's gone wrong? Right, that's correct. That's the image we're looking for, the anti-aliased image. But I was expecting... how is that the front color? And this is the one at the back. Is it front to back? Well, we could do back to front alpha blending as well. Pre-multiply back. So pre-multiply this. Is that the problem all along? Is you're not pre-multiplying... So we pre-multiply the near-miss color onto itself. That might do it. Let's pre-multiply it. Pre-multiply alpha. Let's see if that looks good. It still looks a bit off. Oh, because we didn't set the alpha. Sorry, I deleted the code. So we pre-multiply it. Right, I need to take a look at an image of that to verify it. It's actually fine, but it's looking good. And then we can move on to basically making a very basic model, and then bringing that in. and testing a whole bunch of spheres. Right, so I'm pasting it on top. It's not got any difference. So the problem is it wasn't pre-multiplied on top. Like the front one didn't have the alpha applied to itself. Yeah, it's the same. Sweet. Good job there. Right, so let's go ahead and just commit that, because that's a good place to commit it at. So what have we done? We have got a sphere ray tracer with AA, right? Add sphere ray tracer with anti-aliasing. Oh yeah. So the next thing I want to test is like if we were to remove this entirely, right? How much quicker is it? Because we did it earlier and we was like, oh, if we remove it, it's 0.12 ms. And we did it as, and then we added it as 0.19 ms. But then what happened is we put more if statements in, like this one, so we didn't re-evaluate the color if there was already a closer hit, and it sped it up. So we've kind of lost, you know, the speed gain, the idea of the speed gain. So it's 50% better it used to be. So what is it now? Right, it's now 100% slower doing the alpha blending. That's pretty cheap. If we didn't do the alpha blending in line, it's 0.07 ms, which is about 70 microseconds. And just for a point of reference, to clear the whole screen, it's 40 microseconds to clear the whole screen. So to ray trace 9 spheres, it's only a little bit more. But to do this extra alpha blending thing, it's basically doubling it. That could be okay, because we might be limiting, when we tile this, we might be limiting each screen tile to a maximum of maybe 32 spheres. So it should be, it could be okay. We could be end up rendering maybe hundreds of thousands of these, but I really don't know if that's a good number yet until we actually test the other solutions out. Hey Ray March, how you doing? Yeah man, it's gonna be sweet. Look at this AA, man. Oh, horrible sampled AA from the Zoom tool, but yeah, AA. How's things going, Ray March? How you been? So yeah, here's the real AA. There it is. Yeah. Anti-aircraft gun. That's right. So the next thing is I want to do some models, right? But we're just going to generate some models. So I want to test out a few things with this, right? I want to, put a bunch of stuff on the screen quickly, and so we can test out 1, speed, and 2, so we can test out how things actually look. 3, what's the third one? Yeah, I think that, oh yeah, and to easily be able to place down tons of spheres in an organized way so they look, like they're together. So what we're going to do is we're going to procedurally generate these using sign distance fields. And so we're just going to do the quickest thing. We're not going to make a model structure. We're just going to basically compute the spheres and chuck them into a buffer. And that's what we'll start off with. But we might have to move into lodding at some point where we basically add levels of details of these things. And if that is the case, we might have to think about a proper structure. But for now, I just want to do the simplest thing. And we can have a play around. But we've still got to get like a camera moving around. We've still got to get... so a camera moving around before we do that. And we probably want to have many more debugging rendering things, so we can sort of debug render a lot of this, basically. Oh, how many samples? Yeah, one sample. Yeah. How many samples? 0.5. No. Yeah, we're just in one sample. The basic algorithm is how much did we miss by calculate the distance and use that, and then count this one as, find the closest one that had a near miss, get the distance of the near miss, and use that to get the alpha, and then blend it with a hit. Yeah, so that's the basic idea. So it was inspired by the sign distance field work we did with the 2D, where we basically got it for free, and I was thinking like, surely there must be a way we can get it for free with ray tracing. Well, okay, I say free, but there's a cost. What I mean is do it at the same time as when you render it, because you'll have more context and therefore should get better AA, right? How much you miss stuff, isn't it going to be super expensive for other shapes? So that's the point, is we're not doing other shapes, we're just doing spheres. But yeah, if you had a sign distance, it's basically a cost of the SDF. Like, you already have the distance from an edge when you use the sign distance field. You just got to translate that back into how many pixels have you missed instead of world space. Better than doing multiple samples, exactly. Yeah. But yeah. Right, so let's compute ourselves a model. So I need to have a new buffer, read-only buffer of spheres. So we're going to bring the sphere strut. Oh, lovely, 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 lovely sphere structure. And I want to bring that into GFX. Shared. So this is shared between CPU and GPU. It's just going to dump in ground for things. Here we go. Here's a sphere. We're going to make this CPU side. CPU side, then upload them. For now. But in future, we could probably generate them on the GPU. Well, we can upload like a model that gets instanced on the GPU into a buffer, something like that. But yeah, for now, we're just going to have a buffer of spheres, read-only buffer of spheres, and here they are. And they're also going to have a spheres count. So U32 spheres count. Computation cost is the best cost. Wait till we hit memory cost. Yep. All these spheres are going to have memory cost, and then I guess we'll just pack. And then we'll trade off for a bit of computation. How do you know the with a sign distance field? So basically we do a sign distance from the ray. So we've got our ray. We do our standard check where we have a sort of vector to the center of here, and we do our check to see if we've hit. If we miss, we basically get the same sort of setup stuff. We use trigonometry to sort of like get the distance, you know, get this side from this length and this length. And then we basically know the length, know the radius here. So because we know the radius and the length of this, we can deduce how much we miss by. Then we transform that into near clip space, and then then we translate a pixel from screen space into near clip space, and then transform it out to here to see how big that pixel is. And then if this gap is greater than or equal to, less than or equal to the distance of a pixel at that space, we know it's an miss. Yeah, it would work for SDF only. SDF only, you get it for free. You already have the distance. You already have the distance. You don't have to do all this stuff. You already have that. Like, the whole reason why we did all that stuff is because we needed that. With SDF, you already have that. The non-spheres. If it's assigned distance from an edge, that's all you need to know, right? You can have a shape like this. You have a distance from the edge, right? Like, you don't have the knowledge of it being a sphere. Yeah, but you know, all you need is a distance, right? But by missing by a subpixel will be crazy expensive. So you're launching your array, and you get a near miss, right? But when you're doing ray marching, you're already going crazy expensive anyway, right? When you do all of that. Yeah. I guess, do you early out at a pixel? Anyway? Is that what you do? Yeah, I don't know. Yeah, you have a lot of march steps in here, wouldn't you? Alright, so let's get our spheres buffer. BC spheres equal GPU resource ID ggfx dot spheres buffer ID spheres count. Right, so let's make ourselves a new buffer, people. Yeah, misting would be crazy expensive, yeah. That's true. Yeah, unless you early out at being a pixel. Being greater than if you're less than a pixel anyway, will early out. But then again, all the stuff that near misses by that is still expensive. Yeah. It's very much expensive anyway. Yeah, ray marching is pretty cool though for getting weird shapes. But if you just want a simple shape, if you want a shape that can be defined with maths, then ray tracing is probably better. Yeah, I'm not doing ray marching, I'm just doing ray tracing. So I'm testing every sphere once, as opposed to testing every sphere per iteration. So I'm just given a ray direction, I'm testing every sphere in the world once, and then that's it. Obviously, I need to make that less expensive by doing less spheres. But yeah. Right, so how do we produce... So we can map our GPU buffer. Wait, I didn't even create it, did I? Jumping ahead of myself. Right, let's get this here. Right, buffer initialize spheres buffer. Spheres. So how many spheres are we going to have? Good question. We should probably define some form of capacity right now. Let's just define that here. Spheres. Spheres. Cap. Let's just define it as like 1024. Oh, let's just do a big boy number. 9. Wait. 64K ought to be good enough. So if we do that, times size of spheres. So it's not 64K, but 64K spheres, you know, ought to be good enough. Right. So how are we going to produce these? So the way I imagine doing modeling is that we're basically going to plot spheres on a grid, right? So we're just going to do that, but with maths. So what we're going to do, so we should define an array of coordinates of where we want these things and what sizes, and then we'll just plot them. So we'll probably have, let's start off with, so I should really want to do like thin features as well, I think. Hey Ransom, how you doing? Just had a concert, gonna have a gig tomorrow, then have a week's break. Fantastic. How did it go? Did you have a good time? Yeah, so let's just define a bunch of... Alright, I want to do two, because I want to do like multiple models, right? Hard-coded. So we'll have this sort of upload buffer at the ready. Upload buffer, sphere. So destination spheres. Then we'll have a spheres count here. Okay, equals 0. So we're going to use the spheres buffer, and I want to map the whole thing. So it's sphere capacity times size of sphere. So we've mapped that whole thing, so we can just upload it to the GPU. Boom. And I want to make sure that we're not mem copying. Right. Here we go. So what we're going to do now is define an SDF which makes ourselves a sphere, right? And we're going to make a sphere out of many spheres. That's what we'll start with, and we'll change it a bit. So we need to basically have like a list of positions on where we want these models, right? Positions. So these are all of our models. Do we want them different sizes? So you could have. So things about like a model in it. The way it will actually end up in the end is probably like a matrix, right? Like where this thing ends up going in the world. So for now, I guess, I think we'll just define a strut here and just be like model. And this would just be a position and probably its form of like size or whatever. And then we just have a bunch of models like this. And then what we want to do is just say, all right, well, we've got position of so we'll put it like in the middle. We'll put this one in the middle for now. So 0, 0, and we'll chuck you off in the distance at about 500. Then we're going to then define a size, and this is just going to be probably 100. We should probably call it like a center position, followed by a half dims or something like that. Much easier that way. So then you want to say, so now we can use this list that we can just go over for debugging purposes. And so we have our sort of like, we go over all the models. So for range of index 0, core array count of models, right? So you have all those guys, get your model, call it M, pointer M equal address of index, this guy, right? Cool. Is super linear more linear than linear? Good question. That's funny. So you get yourself a model, and now you just want to just append all the spheres, right? So we've got half dimensions, we've got so our spheres, right? What is the size of a sphere? So we'll just keep that fixed for now. So we have like a sphere radius, right? We'll just do it fixed, and we'll use that as the step. Wait. You plot one per, you know, we'll just do it as one, 0.5. So you plot one per, we'll do them all lined up. Yep. So the shape we're going to define, so if you've got sort of half dims of that, you effectively just want to do your for loop over the Z 0 to half dims. We need a classical for loop. Z equal, so we're basically computing a, we'll iterate from, so should we do like a min max, iterate from min to max. Wait, what am I doing there? Get out of there. Min equal M center position sub F32 times 3 with M half dims max equal add, and you're basically going, oh, min.z all the way to z less than or equal to max.z, then we step by sphere radius times 2. Then that is 1 dimension, 2 dimension, 3 dimension. Just got to sort them out, right? So z's are y's, and x's are, or z's are x's. Cool. So now we're going to place our spheres down. So you basically just get your position for the sphere. So you go, oh, can I get the next sphere, please? I'm going to call you S. That'll be address of so if spheres count is greater than or equal to spheres cap, then we just do continue. It'll be a waste, but we'll just do continue because I've always got to break multiple. Just do continue. Spheres, sphere count, and then you do sphere count plus equal 1, and then what you get is a thing to fill in. So center position is basically you want to get the x, y, z and add a scalar to it. So float 3 x, y, z, adding sphere radius, right? And then what is this? Radius is sphere radius. Then color, and that's where the fun begins. Color is an interesting one. I don't know, right? So we're going to have some debug. We should have some debugging stuff in the shader where we can sort of go, hey, color each sphere differently, using a random color, and color each model as a single color, and just have these debug views. But in terms of a color to do these sort of models now, realistically, when we have some editor, we want to be able to paint each individual sphere and maybe even change the radius as well. I'm not sure about that. But how to express it in this code gen thing is a good question. We could just do position, right? Sweet. That's cool, Cranston. Yeah. It's always fun, like, seeing people getting inspired by the stuff I do, but also scary at the same time. Because, just inspire people to do things. Like change their minds on, like they have a project they're doing, and then I come along and do something, and then people change what project they're doing just to try out something. But then again, I also get inspired by people in the chat as well when they talk about stuff. I'm like, oh, that's a cool idea. And then it sort of infects you and like start doing it, But yeah. It's always great being inspired, but you have to be careful not to throw your current project in the gutter. At the cost of this new cool idea. I've been doing a bunch of geometry stuff lately anyway. The goal is to improve IQs around cone SDF, performance-wise. Nice. That'd be sweet. That's quite cool. That's definitely like a nerd snipe. So in terms of colors, we could just pick one color like we have been doing. We could do a random color per model. We could do a random color per model plus some positional based coloring. Positional based coloring from the center, right, decides how bright it is. It's probably a good idea. Hue, saturation, and all that lot. Here we come. So we got this guy. Here's one I made earlier. Boom. So we'll call this one C. Yeah, I should make a function where it just does RGBA. Can I do another one of these? Because it's really annoying. I've used it many times now. C. This is what I keep doing. Color dot. See, I could do XYZ, but then it won't be GPU friendly. Sorry, CPU friendly, to be used on CPU, which I'm just about to use it on. Yeah, because my compiler has swizzling, but yeah. RGB3. And then we're going to say return C, C, C. Return color.a. Ought to be good enough. Right, so this one does it here, I think. CC, and then it just does with one on it. So we could really refactor all of that. Linear. Yeah, so I could just do this, right? 4, and then 1. So it'd be 4. They're all a bit different, so it's going to be a bit silly, but that's fine. Then CC just goes in there. So that's all the same. Let's repeat that. It's all the debugging stuff for... Yeah, for the UI renderer, where we debug the chunks and tiles, which we're going to have the same thing for the sphere stuff soon. So I want to basically just say this is 4, this gets a 4 after it, that's 4. Did we do ones, hard-coded ones? We did. So that would just be a hard-coded 1. This isn't a 4, that's a 4, that's a 4. That's a 4, this gets a 4, then a 1. Right. The other HSV we did here was more debugging still, so we need to update these with 4s. Yeah, I don't know why I didn't do it then. Do it when I had these. I guess now I've had time to reflect on it. This is basically the same. ABB center, ABB outline, ABB. Right, they're fine. That's the same. Debug draw tile draw command. Tile draw command. What? Visualize the draw commands, right. Okay. Excellent. So we got that new lovely bell and whistle. So the shader's compiled just fine. So we just got to get this in here. So we're going to do a lovely HSV to RGB4. Then we've got to convert it back into, I forgot now actually. Right, so let's get this in. So the hue is gonna be basically some like playing off of what number are we playing off of? The model index. So that's the hue. Then the saturation and value. Saturation can just be 0. It can just be fixed, right? 0.6, something like that. Yeah, but then I want to play the value, like the brightness of it. We'll make it darker as it gets towards the center, right? So we can do that quite easily. We've got our position here. So we just take the center position, we do a length op, right? Also we sort the music. We do a length operation, and we're going to do that with like a subtraction going to, it doesn't really matter, but yeah, going towards the sphere that we've just plotted down, and the center of the model object. And with that, we can use that number to define how bright it is. So, and the alpha we want is 1. So f32 times 3. So that's not going to give us 0 to 1. So what will give us 0 to 1? So we've got half dims. So then we want to do like divided by max element of half dims, right? What's the maximum one of those? And that'll be the radius, right? So that'll get us a nice color for the sphere, but then we're not really got it in as a U32, we've got it as a float 4. So then we do the whole sort of like pack. Yeah, I'm not really fond of this name. But yeah, packs to a U8 times 4, which is just a U32 from a, yeah, I'm not really sure if I like the name. Or is it unpack? It's packing. Huh. Yeah, remember I didn't have it in the header file. But I thought I fixed that in S8, pack S8, unsigned, there we go. Yeah, there's just a bit of a, ooh. Yeah, that was a bit of a copy paste error. So can I see if I can fix that in my main HTTP? I swear I fixed that. It was just in the header, it wasn't in the implementation code. Pack, unpack. Lib, hmaths. Vector.h, is that right? Pack U8. Yeah, oh, no, this one's not sorted out. Damn it. That one's wrong. Yeah, so I did sort it out here, but I didn't fully. Right. We need to make sure we put that up. That's cool. All right, so that should be everything we need to get the model in there. Does it compile? Right, so I don't think we're oh no, we did. Right. So now the model, now we have a buffer filled with spheres. We're filling in all the things. We've got a buffer with spheres, and we'll do the cap check. Fantastic. So shall we now do the shader code, right? So what are we getting? We're getting 200 spheres. Yeah, I wanted to make sure this doesn't make my GPU crawl to a halt and then stream dies. So let me just check. 200 by 200 by 200. Bit big, isn't it? So let's make it a little bit less resolution. Let's just do 10. So it's 10 times 10 times 10, which is 1,000. So it's 1,000 spheres per pixel, which means, you know what, let's just do, can we do less? I want to make sure my GPU doesn't die. Let's do 4. It's just 4 times 4 times 4. That's more manageable. No, it isn't. It's half dimension, so it's 8 times 8 times 8. That's a good enough number we can work with. And then we'll go from there. So it's going to be a super small model. So in the shader, all we're going to do is literally do this, right? Where's this spheres count? We get rid of all these test spheres. Goodbye to you. We use the bundle constants, which is like push constants. We get our spheres count out from there. And then we go over all those spheres. Now, we then go to BC spheres and get our spheres from there. And yeah, so what could go wrong is the question. All right, here's for the time. Right, so I'm going to run a poll of would it crash and burn? You all saw it. I'm going to run it for 2 minutes. And I'll be back in 2 minutes. BRB. Wow. 5 people, 71% of you who voted said no. Probably because you've seen how many crashes there has been. But everyone likes to prove people wrong. Yep. Right answer would be Seg's fault, yep. That's it. Oh wait. No, the question was, will the GPU crash? And everyone said no. People believed in me. People believed it. That's amazing. I don't want to let you guys down. Right, we got a Seg fault. Okay. On a set. But yeah, we'll this doesn't count. Let's say that. This doesn't. Ding 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 ding. Yeah, this shower glorious. Let's do it. I'm now following him. What? No, it's not follow. What's going on? So where's this thing going? Where's the thing? What? The upload was called must come before frame start. Right, this is a GPU limitation. Yeah, technically my upload stuff is a little bit wrong. It shouldn't be doing this. Where am I going? This is fine. We're going to move this up a bit. Technically it should be in between frame start and frame end, because if it's outside, we should be triple buffering our upload buffer. Or what's the other thing we should be doing? Yeah, because currently the GPU could be using this buffer and we were writing over the memory. So we haven't encountered that problem just yet. But yeah. Technically it should work like the readback does. But it's not. Right, see how this goes? Holy moly. 12 ms. Running slow. Holy moly. We're not double buffering it. Wait. Upload buffer is the double buffer. Upload buffer is the double buffer. Go over all the models. Why aren't I seeing anything? Is the XYZ wrong? 0x0y off into the distance. Our sphere radius is very small. If we make the sphere radius bigger, let's make it 10. And if we make it 10, then we could say, make this larger, like 40. Or maybe let's make it 20. Let's do 2. So it's going to draw a 2x2x2 grid. Right, why don't I see a 2x2x2 grid? I'm not sure you missed, Ransel. I'm not sure when you disappeared. But yeah, we've just got the model code set up, basically. Got some model code. Yeah, so we're just generating basic models. And currently the model is a 2x2. Well, currently it's just a 3D grid of spheres. But we're trying to figure out why it doesn't want to work. So we've got the spheres, we've got the models, just one. Half dimensions is this, we're stepping the distance. Sorry, they got a radius of 10. I should probably do 30 or 40. Right, it's 2 ms, it's quite slow. This is fine. So we're definitely packing some down, right? It's reading the data out. Sphere, sphere buffer. We need to do synchronization code. That's probably the issue. Read only. Nope. What else? Center position, half dims, min, max. Go over min to max, min to max, min to max. Increment by this, yes. Sphere. Put the sphere on, which is just XYZ. Add that. Well, that looks pretty sensible to me. Although we should probably just bake in a white, right? And if whole screen goes white, I apologize in advance. So let's just do grey, actually. Yeah, I don't think I need a flush. But yeah, I think my memory upload API is a bit buggered, but it works fine for the UI code. So I don't know what the problem is. Aha, it was the color that was wrong. Guys, it's happening. Right, there's the model. Getting a weird sort of thing there. Why was the color wrong? Can I render my UI again and see if that works? Right, the UI still works. Yeah, magnetic balls, all magnetic. Hue, saturation, brightness. Is the brightness 0? So if I hard coded that to 1, deleted that. Urgh. What? Color XYZ. That's what you would expect, right? Hue, saturation, brightness. Why? Is it the packing code? Oh boy. Clumsy 01 multiply round. Shift left. Alpha high bits. Oh my days. I thought I solved that problem. This is annoying. Can I get the latest version HCC library stuff over? Because I thought we fixed that. I generally thought we had that problem solved. Sorry. Game engine, third party, HCC, libhmaths. Right, so we'll do a git diff or git status. Git diff. Yeah, it's done all these or sorted out all these ors. That was a typo that I had. Right. Good. There we go. There's the balls. So we should probably bring them down and a little. I don't know. It's also got quite slow. We've got to figure out how many balls we've got. So say negative 200. We'll then say negative 200 on the x as well. We just want to see all the balls, right? Okay, so we've got there's the grid. Not quite the color I was hoping for. In the middle, it's going to be... Right, hue saturation value. 0 is dark, 1 is bright. Is it white though? So the further away it is, the more bright it is. So I probably want to then multiply the final result. We basically just want to keep it, lock it in a range that we care about. So you say divide by 0.5, so it gets you 0 to 0.5, and then we probably just plus it by 0.25, and that'll bring us between 0.25 and 0.75. And that'll be more of a nicer number, right? We can get the blacks, we wouldn't get the whites. I know something's still a bit off. Why is it darker? Oh, because of the lighting situation or something. But yeah, there we go. Ta-da. Right. So, how many balls are we going over? We've got a 5 by 5 by 5 grid, right? 125 per pixel. That's what we're doing. So, and that's still running the same. Yes, there's 125 per pixel. So there might be a benefit if we did sort them. We could probably early out, right? And then if you sort them by depth, you can early out. Which means less expensive calculations. But yeah, 2.3 ms. You know, if we were to bin these by tile, you should hopefully get you'll get less, right? But the problem is, as we're seeing right now, is you're getting even the ones that are behind are still trying to be rendered. But obviously, we could do lodding where the further away they are, the bigger the spheres are. So if it's like a proper, you know, imagine if you push this model really far off into the distance. Let's put it at 10,000. Maybe further, 100,000. So obviously here, like each of the balls are all like kind of like a pixel, and it's, I don't know, it'll probably look quite funny when it moves around. Maybe at this point you want to have just like one big sphere. I don't know, maybe a few bigger spheres, and as it moves it will sort of like, I don't know, but then it might pop. I'm not sure. I don't know, it depends. When your spheres go smaller than a pixel, maybe you go up to the next LOD. But then that's still, yeah. No, we don't break out the loop yet, because we can't break out the loop because we don't know which one is, we're not going from front to back order. We iterate over every sphere, but we don't know what order they're in. So should we see if we can order them front to back and then do some layout code? Because I think that'll be better. So to do a depth, it's simply, you can just do this, right? These two, and that'll get you a squared distance in these two sort of quote unquote operations. And then you can sort the sphere based on that. So if you had all your spheres in a tile, for a tile, you can then sort them per tile. And you could probably sort them in a multi-threaded fashion, where you use every thread of a tile to sort all of your spheres. I think I've seen a thing by AMD. They've done this sort of thing before, where they've got it. So maybe we should look at that code if we can't find a good GPU sort, because they've already done it there, I think. AMD is these nuts, exactly. Exactly. Welcome, Type Beaver. How you doing? GPU sorting algorithms. So effectively, we want to use all of the threads to sort of help this sort. You've heard of this Bitonic sort? It's interesting. This guy's called Davos. There's a guy who hangs around in the chat called Davros. Very similar name. Easy to get confused. No bubble sort. Oh my days, it's not even exist. What? Checks for save version? Urgh. Oh. Quadratic sword, man. Improve GPU sorting. There's also like a sorting library from AMD, but who wants to use libraries? Where's the fun in that? Thank you. We got it, guys. Wait. There we go. Much better. Sort code. Fix. Bit onyx sort, or is it bitonic sort? Good question. Is there anything to do with, like, you know, 2? Power sort diagram, it was used as a construction method for building sorting networks. So the biggest problem, right, is, so if we sort it per tile, it's probably less data you're sorting, right? But if you're sorting it per tile on the screen, you probably need to have a maximum capacity per tile. And if you have a world filled with spheres, it's going to become so easy to yeah, I think we need, if we're going to be doing this ray tracing approach, we really need a way to reduce the numbers of spheres, right? Like, that you're just clearly not going to see. Like, if we're going to be building stuff where it's like basically this, right? We're obviously, you know, I'm not sure they're going to be perfectly aligned like this. That we might offset every other row or something, right? Give it a bit of so it's not gridded perfectly. It's not uniform, but still have some form of pattern of some kind. We have to have a way of saying, you know what, these guys are just not going to be visible. Yeah, it is kind of like that. Bitonic, yeah, it's probably bitonic actually. Bitonic sort, one of the oldest parallel sorting algorithms, is simple and works especially well for small to medium-sized data sets when the number of elements to be sorted is a power of 2. Ooh. Nice. Parallel radix sort is a non-comparison based sort and has been shown to be very efficient on GPUs, particularly for large data sets. Yes. That's one the AMD folks have, isn't it? An implementation of. Reminds me of Minecraft where you want to render faces you don't see. Exactly. So I think that's one of the problems we want to solve if we're going to be doing the ray tracer, right? If we're going to be doing the ray tracer, we want to have a way to sort, and that's known as like occlusion. You want to have like an occlusion pass, right? You want to basically predict which ones aren't going to be visible and just don't render those. I think that's going to be a big gain in performance because you just don't include those spheres in the buffers at all, and they won't get sorted. They won't get tested per pixel. They won't get binned per tile, right? So it's a way of filtering out a bunch of information, especially when you want to make these guys pretty diddy, right? Or potentially small. I don't know how big they want to be, but yeah. Regarding the name Bitonic, from Wikipedia, it looks like it comes to monotonic, which means increasing or decreasing. Oh, but bitonic increases then decrease. Right. There's probably bi then? Bitonic? This ray tracing is all the... No, ray tracing is not the only way. Oh, okay, cool. Yeah, ray tracing is a technique you can use to, yeah, to render. You can also use it to do lighting, simulate lighting. But yeah, there's a lot that goes into rendering. Like, there's quite a lot. As Cranston's saying, there's like basically, yeah, lighting model or material model, that sort of thing. I'm up to programming, but could you do a blanket raycast initially to test which spheres have been detected by the camera? So that's another thing we could do, is we could do like a... See, the thing is, I might be... Can I show you some bits of fun I'm thinking about doing? Do you want to see something fun? What's this? Um, uh, oh, hopefully this is not too fast. I wanted to nail it first time. Oh, I was hoping that to be more effective. Give me a second. Hold my beer. But yeah, I'm hoping to animate these guys, right, and have some really sort of organic-y sort of like feeling with them. So, what was I saying? Yeah, so it kind of would be cool to like have a way to sort of like maybe you can group them, like you have a model. If a whole model obstructs another model, then you shouldn't render it, right? So there are ways to sort of do a sort of a coarse culling. But you're saying, could you do a blanket raycast that initially tests which spheres have been detected by the camera? Right, so what you're saying is go over all of them, do a test. But then you need to do it kind of per pixel. We're already doing it per tile. Wait, this is 125 per pixel. Our tiles are going to be 8 by 8 by 8 in size, right? So if our spheres, like if we were to have 8 by 8 and go through there, 8 by 8 pixels, we're probably going to hit a very small number So it could be fine. And it might not matter. And also, are we seeing hard edges? It's cool that you can basically use all the conventional speed up techniques from ray tracing, frustum culling, depth pre-pass, deferred shading, and light G buffers. That's another way to do it as well. Yeah. I'm not sure if I want to do G buffer though. I'm not sure. I want to try and maybe do a bit of a forward. What's going on here? Oh no, that's done. So I think we've got a bit of a problem. There's something that's wrong with this. Maybe the distance algorithm from the... Yeah, we're going to look into that. But yeah, I think what might be good is like if we put it into tiles and then put it into tiles and have a maximum size of like have a maximum capacity on the tiles, like, oh, we can only have what's this number, 125. So maybe we say, oh, we've only got per 8x8 pixels, we say we have a capacity of I don't know, maybe only 32 per tile, something like that. And then the rest you just ignore. And maybe that's good enough so we don't have to do any of the optimizations. And the tile binning is just enough. But maybe, yeah, it depends how much it costs to do the tile binning itself. I think that's a good next step. But let's fix up this anti-aliasing because I think it's a bit wrong. So we will remove this thing. Is there anything that's looking painfully wrong? Yeah, those ones there, these little dots, they're a bit weird. So we'll turn on the AA. If one near miss color here's your boys. Right, I've got to figure out where the problem is. What? What? Right, so you're seeing 2 pixels there, right? So if we look at that when we disabled this, retake a screenshot, throw the bugger over here and see it change. I didn't copy it. Right, there's an issue. And there's another issue. So I've got a near miss. That's kind of right. I got a near miss. There's the outline. But I'm very close. But then why are those ones more transparent? It's really weird. There. Yeah, I'm not sure what I want to do with this ray tracing anymore. Yeah, I think the next thing we should do is binning. Bin them per tile, because we're going to do that anyway. And then put more models out, have a cap, and just see how it would look. It grabs the near color, which happened to be super dark. It could be something with the normal. I'm not sure though. So the way we can know that is if we hard code the normal to opposite of light direction. And that will let us know if that's right, you know? So where's normal? So we hard code the normal to negate of light direction. That will tell us. Oh. What's going on? Do you want to give light direction? Or is it the same direction? Yeah, I think that's better. I don't know. Didn't really think about it, to be honest. Right. Huh. Only changing the ones on top? So maybe it was right to negate it? Closest point on sphere. Oh, we can color based on the alpha. Right? Where we make it fully opaque. So you simply just have, you have a white color and you have your square root. Damn it. That should be your alpha in it. One take. That one. I didn't even enable it, sorry. Pre-multiplied, shoot. No, I want to overwrite it. Are we looking for full-on coloring or? Yeah, I think I want one alpha. So something like that. I don't know if that's right. Let's see. Didn't copy it. Right. Interesting. What are we getting? So this is a good debug visualization. So what we're seeing is we clearly are getting probably, yeah, we're in correct lighting, but this one is not getting, the pixels there are lighter for some reason. Oh crap, I got rid of the, there we go. Oh, I meant, oh, shoot, I got rid of the other image. But yeah, so we're seeing something, right, let me get the other image back. Render, screenshot, paste this one over. Perfect. So the next debug visualization we want to do is debug visualize Could we relate to the fact that the ray seemed to be close to 3 spheres? Let's check. Right. So it near misses this one, hits this one, right? Near misses this one, hits this one. And we see the near miss paint happen there, right? But the near miss depth could be further away. That might be it. Could be further than the hit by some epsilon amount. So that's what it could be. Yeah. Is it because the lighting is the same on each sphere? Does it carry to the next? No, it's not nothing to do. Yeah, I think it's something to do with the fact that we've got. Yeah, the lighting is the same, but the problem is this is darker, this is lighter. We should be seeing a smooth anti-alias line around there, but it's grabbing the color at the back and not. Is it though? It seems to be doing a sort of a smooth gradient there, going down. Not really sure exactly. Should we try an epsilon? I'm not sure if that's a good epsilon. Right, that did nothing. 1, 0, 1. I need a thing in my engine where we just take a picture of the screenshot, put it in the clipboard. Do a screenshot, put it in the clipboard. You know what I mean? That would have been cool. Yeah, so I don't know if it is that. We could try 1. That's quite big though. It's nearly the size of a whole sphere or something. But it's a good test regardless. Right, still not fixed it. So I don't think it's a near... Yeah, I don't think it's anything to do with this. But we definitely get a near miss on it. Could it be the normal? We can color it based on normal. That's the next one. So we can color based on normal. Return. So Marles. So we want to put like the normal in here. Normal.y. Normal.z. With probably a 1. Yeah, so we'll just use the XYZ. Yeah, so the normal is -1 to 1. We've converted it into basically 0 to 1, right? Snorm to unorm, and using that as the color. Rightio. So what we're looking to gain from this is see what the normal is on... I don't know actually. Yeah, this in conjunction with another one. What do I want? I'm seeing the normal color without any alpha. So the other one is just set all the alpha on because I want to see it. Right, so the normal seems pretty sensible there from the miss. Right, getting that normal on there. Why is everything seeming sensible? Do we get a proper normal? Then if we alpha blend that with the like, is that still wrong? Sorry, that sets the color, isn't it? Yeah, so we disable that one, it will alpha blend it in. Does the problem still show? It still shows. Near miss, near miss. Yeah, I think you could be right, Cranston, actually. What you were saying. This here, pixel right here, they're both near misses. And then we're grabbing the solid hit. So I think this is the way I was thinking about doing it first. But then I never did it and it hits the one behind. That's it. Right, I think we found out what's going on. So what we might want to do is say, you want to upgrade it. Like, if you found a new near miss which is closer than this near miss, you check to see if the near miss is closer than the hit. And then you copy the color over and make it a, so it'll be something like this. It'll be a bit hacky, but it'll solve the problem. It won't support transparent shapes though. Transparent. I need to move it earlier. Or that later, rather. So if this near miss is closer than the hit, make this the new hit. Or make the existing... Shoot. No. Make the closest hit this thing, then just give it the color. Set the alpha to 1. Bit of a hack. But it should do. Whatever it was. Oh. Near miss color. Yeah. Well, that should be the fix. I don't know, I can't really tell from here, so let's copy it in. Oh ho ho. We did it. So we just make it solid. Right, even if it... So it's a near miss of a near miss. Yeah. Boom. We need a bomber salute. Get the bomber salutes going. Boom. Oh yeah. So yeah, it's because we got a near miss and another near miss, and then it was selecting the one behind that because it was a hit, and the lighting was off. Still getting a little bit weird there. But I don't quite know. And this got made worse. Pixels are hard, man. You saw out some pixels and other pixels like, no, mate. Old, new, old, new. That's good. But yeah, it's still better overall. Yeah, it's better overall. Yeah, overall it's a better image, which is a good thing. Like here is it here. Like there's the old one, there's the new one. There's the old one. There's the new one, right? Overall better image. Just so I understand, after the first near miss, we treated any subsequent near misses as full. Yes, as full hits. Yes, that's what I've done. So we've not. Yep, that's correct. So the problem is now is that the transparency, like I can't have a transparent sphere with the way I've done it as a bit of a hack, but I can always sort that out because I just set the alpha to 1. So what we do here is we say, I'll put the comment down. Old closest miss is being replaced and is closer than the closest hit. Replace the closest hit with the closest miss we are about to replace. Overwrite. Come on, that's it. Yeah, maybe if we did the sorting logic, we wouldn't need that, and it would be more correct because we would be doing the alpha blending in place, right? And we can early out a fully opaque thing. That's an interesting thing. We're doing it for the UI already, and it does give us speed boost. So yeah, that was pretty successful. So in the next stream, we're going to be making a bit like the UI, right? Tiled and chunk rendering, right? We're basically going to be doing copying and pasting the code. So if I go over to like UI, source UI shared. Here's the chunks. Let's just get some UI on the screen. So we're breaking them into chunks. As you can tell, we've already binned some on the left and some on the right here. The rest of them don't have anything in, right? So we have chunk binning, and then we'll be doing tile binning, where we bin them into tiles. And as you can tell, these are super small, and we'll probably have 32 per tile. So as you can tell, they obviously go into multiple tiles, but that's fine. But yeah, we should get a massive speed boost basically, right? It'll be fast. I'm not sure how many are here, but given you've got 5 going backwards, at most you'll have 5. No, you could have more, because technically at most you'd have probably 10. But 10 is a lot less than 125. Right. Yeah, maybe we need some occlusion thing. I'm not sure, but yeah. So that's pretty sweet though. That's a good next step to do because we will definitely... It will stop... Like currently the GPU is not capped. When we bin them into tiles, we can cap it per tile. And then we can basically say this is the slowest it will go. And we will get the slowest it will go, and at worst we'll get visual artifact like issues when we've simply not rendered a sphere and it's actually in front of all the others. Like that's possible. Yeah, so we'll do the binning first, and then we'll think about the rest of the things. Yeah, the hope is, right, that this ray tracer could render... Like, I'm not sure what my aim is, right? Could it be 1 million? Is 1 million spheres enough, or is that too much? Can we make do with 500,000? And if we render 500,000, how fast is it? Could we render it from multiple angles and do lighting? could we, all these sorts of questions I want to try and ask and answer. How much MS are you shooting for with the ray tracer? So that's a good question. Presumably we want to have lights, right? So you need to be able to light your scene. So ideally we need to be able to support lights and shadows, right? So ideally we need to have multiple essentially camera angles, right? Depending on how I want to do the lighting, I'm not quite sure. I need to do a bit more research, but we might have to render it from the perspective of a light. And maybe render a depth buffer, or maybe just light the actual objects in the scene. So if we're doing that, we need to be able to at least it needs to be like pretty quick, right? Or maybe, yeah. So if we say can render 500,000 spheres, and we can say, I did some calculations earlier, and this obviously doesn't account for reading spheres from buffers. This is on the Discord. We just did some very quick maths, which doesn't include reading them from buffers and also the tile binning. There's my face. So currently this is based on 9 spheres per pixel at this MS. We actually got it lower. So expanding it to 32 spheres is this much, 0.6 ms at this resolution. This is the resolution we're doing right now. So technically then, if we're doing 32 spheres per pixel, because we're going to bin them per 8x8 tiles, theoretically we should be able to render 600,000 spheres. And it would only cost 0.6 for ms. That's not counting from fetching it from memory. But we'll see how much that has an effect. So yeah, that's the basic gist of things. And plus, this is a bit of a smaller resolution. I don't do 1920 by 1080 as well. So yeah, gotta have a think about all that and see how good the numbers are. Right. Not counting the binning time. Yes, that's not counting the binning time. We should probably include the binning time, although binning was pretty shoot. We only tested 2,000 objects in the UI. Yes. Yeah, I've got to have a play with the binning. See how fast we can make it. But yeah, right, let's have a quick plug. So I'm going to be putting up the code up onto a GitLab. For people who want access to that, they can follow the link there. And there's a channel on the Discord. Right, we also have a Discord where it has all the instructions on how to sign up and get access to the code. Yeah, it's best if you support via Ko-Fi. Would appreciate that, because Twitch takes 50%. I'll next be streaming on Thursday. We'll be streaming for 2 hours. 8 PM GMT +1. And yeah, we'll be doing the tile and chunk binning. I'm sure we'll be able to write it in those 2 hours because we've already got the code. And then we'll be able to probably get multiple models up on the screen and just put them out in the world and just see what we get. We could probably just spawn a whole ton of them. So that'll be on Thursday. And I also stream on Sundays as well. I also have a Twitter as well where I post updates if you want to get text form updates on what goes on every stream. So yeah. Also, Cranston, I noticed your website doesn't refresh for me. I get a timeout. If you can fix that, then I can maybe get you on an update for your scripts. That'd be great. Yeah, thank you. Right, it's fun to read. Yeah. No. Do you rate TJ? Hey, TJ's rasterizing things. Is he rasterizing? I don't know. Good TJ. Right. Yeah, have a good Wednesday and Thursday. I'll see you all Thursday. Thank you all for coming. Good stream, and I'll see you on the future one. Much love.